Hi, this is Bernard Brault, and I want to talk a little bit about Fourier Series, Fourier analysis, spectrum analysis in physics, engineering, and in science. Quite often what you have to do is you got to do Fourier Series. It comes across all the time, and I never like the way they teach it because I don't think it's very intuitive, and I think I have a much better way to look at it that I want to share with you. Hopefully it's going to help you understand Fourier Series in a different way, and possibly even help you out to understand it. So if you look at it from a textbook, here's they show you a square wave here, right? And then doing the Fourier series amounts to calculating how much of the sine wave that a square wave contains, and how much of a sine wave of twice the frequency as the red one, and 3 times and 4 times the frequency. So you're looking at certain sine wave and all of its harmonics, and you're asking yourself, you know, how much of each of these harmonics do you have to combine to be able to recreate the square wave? And the value of each one of these harmonics is basically the frequency response, or the frequency content, or the frequency spectrum. And there's all these different names meaning the same thing. And in theory, there is a way to calculate this, and this is a formula right there, the 1 over L, the integral of 0 to 2L, and it gives you this sort of complicated integral formula. And eventually at the end it boils down, if you do the math, that you know, it's going to be equal to 4 over n pi times 1 for all the odd frequencies and 0 for the even frequencies. All right, so this is the math way of looking at it. Not so intuitive. All right, so let's look at it from a different perspective now. I'm going to start with something very simple: points on a map. All right, so when you look at points on a map, this point is going to have a coordinate, and that coordinate is given as how much you have to move in the east direction, right? That's going to give you the x0 coordinate, and how much you have to move in the y direction, so the y direction. So you start from a reference point, and every single point on the map here can be represented by two values, and this is basically the x and the y coordinate. Of course, I'm sure you can imagine that if this was like a point in space, you would need a third coordinate in z, or height, and then you would have 3 coordinates, right? So far so simple, and we can express those 2 numbers there. We refer to that as a vector. So this is a vector. Don't think of a vector as an arrow, but think of a vector as basically a set of 2 numbers. Now, if you were to change the frame of reference, so I'm showing here magnetic east and magnetic north, and here's the same point. So depending on whether or not you're looking at this point from a reference of true north, true east, or magnetic north, magnetic east, then of course you're not going to get the same coordinates. So really the coordinate x0, y0 only makes sense when you explain what is the frame of reference that you're using. If you're using the magnetic frame of reference, then these 2 digits are not the same, but they do represent exactly the same point. We're not talking about a different point. The other thing that's common between the two is whether you calculate the length of, you know, the distance between the origin and this point, regardless of the frame of reference, you're calculating the same distance, right? So that's pretty common. Now the question is, how do you calculate the x prime and y prime given the x0, y0? And there's a very simple way of doing this, and you can almost see it right here, and I'll show this to you. But so calculating the x prime, so in other words, what are the coordinates in the magnetic east? What you're doing is you're looking at the point, and you're looking at the shadow of the point. How much does it project? And that's the dotted line that you see there on the magnetic x-axis. So, and in order to do this, there's a easy math trick, and you do what's called the dot product, or the scalar product of the 2 vectors. So you're taking this point vector x0, y0, and you're doing the dot product with a unit vector in the east direction that I refer to as xe, ye, and once you do the dot product between those 2, you will obtain that value. and that's what I'm showing right here. So you take x0, y0, and you do the scalar product with the vector and the magnetic east, and you obtain that value x prime 0. So how do you look? So the way to look at this is to look at projection. What is the shadow of this vector along this axis right here? I wanted you to notice just a few things here. Is that, of course, if you were to look at what is the shadow of a vector onto itself, obviously it's 100%, right? So if it's a unit vector will sort of shadow on itself with a value of 1. How much does north shadow east? 0, right? Why? Because these things are orthogonal, or they're square. So if you look at the shadow of north on east, it's 0. So orthogonal vectors do not shadow against each other. Okay. Now the next thing is you want to look at what is the y-axis, the y component. Well, it's exactly the same way. But the way you calculate the y component is this time around we're going to look at the projection of our original vector onto the y-axis, or the magnetic north axis, the new magnetic north axis, right? And that's about the trick. So let's go back to signals now. You look at a square wave here on the left, and I'm going to represent this square wave as a vector, but not a vector of 2 dimension or 3 dimension, but a vector of 16 points. And those points are going to be just values at different time. So it's value 1, 1, 1, jumps down to -1, -1, -1, -1, jumps up to +1, +1, +1, and that's what you're seeing right down there. So basically this vector here represents the square wave that you see right there. Triangular wave, more or less the same way. Probably going to split the time into 1 to 5 different time slots, but I'm ramping up from 0 to 1. That's what I'm showing right there. And then I'm going to go from 1 down to 0 and -1. So this segment right there is represented by this right here. And finally going from -1 to 0 right there is this right there, right? So this is a vector. Again, it's a vector. Remember, you always have to say what is the frame of reference for the vector. So the frame of reference for the vector here is basically the time at t equals 0, the time at t equals 1, the time at t equals 2, and so on. Where when we had geometry and we had like a point, well, it was how far do you move in the x-axis, how far do you move along the y-axis, right? So let's focus now on changing, the frame of reference. The same way as we changed from true north to magnetic north, this time we're going to use a radically different frame of reference. And we're going to look at it just for the triangular wave for a second here. So you got this triangular wave, and what you're asking yourself is, okay, so this is a triangular wave. This is my frame of reference, which is my unit vectors, if you want, in the x-axis, my unit vector in the y-axis and the z-axis, and of course it goes on, and I'm going to have a new frame of reference, and my new frame of reference will basically be different frequencies. So at frequency 0 is DC, and there's no DC component here. As you can see, it's as much above 0 as it is below 0, so it's 0. So frequency 1 is a sine wave of frequency 1, let's say 1 hertz or 1 unit of frequency, and then the second one is twice the frequency, 3 times, so a multiple of this fundamental. These are all harmonics, and the question I have is the same as what we had before when we had the point. So we were like, how do we calculate the new coordinates? And if you remember, we had a trick for that, and the trick was the projection. It was how much does this triangular wave projects on a sine wave of frequency 1 will give you this value. How much this triangular wave projects, is its shadow, what is its projection on a sine wave of frequency 2 will give me that second value. So I did this a little more elaborate way, and that's what I'm going to share with you in the last couple of minutes. So we're back to a square wave here, right? And that square wave is shown right there. It's a vector. It happens to be a vector of 628 dimensions. Don't be afraid about the 628 dimension. You don't have to visualize this in hyperspace or anything like that. It's 628 points, and it's a value of the square wave at each one of the points. So half the time it's got +1 value, the other half time it's got -1 value, and that's all there is to it. Now I got a sine wave here of multiple times a fundamental frequency. Here's a fundamental frequency. I'm going to put, n equals to 1, so this is n. So when I put n equals to 1, it gives me this frequency right there. And if you remember, the first coordinate of my Fourier transform is the projection. How much does this square wave projects against the sine wave? And we had a way to calculate this. It's so this is a sine wave, this is a square wave. So how much does a square wave projects onto this? Well, you have to calculate this times this plus this times that plus this times that. Remember, you did the x0 y0 plus x1 y1 plus x2 y2, the dot product that gives you the projection. So I did the math for you, and then what I get is a value, and I add them all up. So this is basically this times this times that, and then I add it all up, and it adds up to 399. But remember, I said you need to project against a unit vector. So that sine wave, if I were to project the sine wave onto itself, and that's what I did right there, that's a sine wave projected onto itself, and it gives me a value of 314. So really 314, that means that 399 has to be scaled with respect to 314 because that's not a unit value, right? So 399 divided by 314, and that's what I get right there. So I rewrite that 399 right there as 400, 399.999, 400. I divide by, this, and I get this value. If you remember earlier, I picked up from the website a formula to calculate these Fourier coefficients. And I put here the theoretical value. And if I were to go back, let me just very, very quickly show you what it was. This is where it came from. It's 4 divided by n pi. That's the theoretical values. And here's the theoretical value. And it's 0 at 2. And it's this value, 0, this value, 0, that value. Right? And here what I'm doing to get this is just simply, to get this value is the projection of the square wave on a sine wave. If I want to look at this one there, I need to project against something that has 3 times the frequency. So if I go 3 times the frequency, I get here a projection of 133. I scale it with respect to 314, and I get this value 0.4244, which matches the prediction, the theoretical value. Let's do it for 9 right here, right? So I'm going to use a sine wave of 9, and here's a sine wave that's 9 times the fundamental frequency. And now the question is, what is the projection? What is the shadow or the projection of this square wave onto this new sine wave? And the value is 44 divided by 314. And there it is. Oh, sorry. So this was 9. I'm going to put 44.43. And I get 0.1414. Look at that. 0.1414. Let's do it for 11. One last one. 11. What do I get? 36. I'm going to put the 36 right here. 36.35. And what do I get? 0.115, 0.1157. See this number? That's the calculated number here by the projection, and this is the theoretical value. So, bottom line is, what are we doing? We're calculating the new coordinates, right? X prime. So what is so this is the value of a square wave. These 600 numbers. That's the value of the square wave. And what we're doing is calculating things using a new way of looking at it, using a new basis. And those are the coordinates right here of the vector. and I would have to go on and on and on like this. But you see, I found a way to calculate these, and they are projections. All right.